So now we came to this part, which is the exploration and exploitation, which is a very interesting part for an agent to know is it going just for a goal directly, or is it going to explore the environment. It is very important for the agent to know how to determine that. So an exploration, as we mentioned earlier, is exploring the environment to find out the information about it. And exploitation is the act of exploiting the information. It is taking the information from the observation part and in order to maximize the return, I mean, to get more rewards and to achieve the goal as fast as possible. Since the goal of the agent is to maximize the expected return, so you may think that we want our agent to use exploitation all the time and not to worry about the thing of the exploration. And this strategy is not always right, which means here in this the lizard, if it just goes direct to these 5 crickets, that's it, finished. Yes, it is. That is the goal, but it is also better for this lizard to know if there are more lizard crickets in this area because we do not know. So since we do not know and we want to know, and here we will balance between the exploration and exploitation, and that will lead us to another term which we call the epsilon greedy. Epsilon greedy strategy. Greedy means being stingy, or you want to learn more. So to get this balance between the exploitation and exploration, we use this which we call epsilon greedy strategy, which is shown here, to balance between exploration and exploitation. If the epsilon equal to 1, it is 100% certain that the agent will start out exploring. So at the first start point, the agent will go for exploring. It is not going to just directly, I mean, it is not just going directly to do actions in purpose of doing actions. It is going to explore the environment and to know the best actions with the best state, which will be known from the best rewards, and then will determine which route or which path will be taken. So if we take a random numbers equal bigger than the epsilon, once it is going bigger, so it is going for the exploitation, and that will only be after the choosing active via exploration. This is actually a code using Python. So this is the code will be used as a function representing this epsilon. So also this diagram representing this epsilon. At the first stage, we going for exploration until it explores the environment. So it goes for the exploitation. So it uses the explored information and going to choose the best path. But how to know which is the best Q value and learning rate? Again, back to this equation. To update the Q value of the action of moving right, taken from the previous states, we use the Bellman equation that's highlighting previously this equation. And with this example, I think the whole method will be very clear how to update the Q value, because now we are having this Q star SA, and we keep updating this Q value until we achieve the best QSA. We know this is the best action and this is the best state because it gets the best rewards and the expected rewards. This is the best method or the best actions to be done to achieve the best and the fastest way to reach to this goal. So we want to make the Q value of the given state and action pair with the clues as we can to the right hand side of the Bellman equation. To the Q value will eventually converge to the optimal Q value. So again, going to this equation, this is what happens for the time with comparing the losses between the Q value and the optimal Q value for the given state action. So we have this Q value, and here's the optimal Q value, will give us the losses. This is the equation 1, the Bellman one, and here's the optimal expected return value. Summing them will give us the losses, how far we are from the goal. And this is going to be clear from this learning rate. How good are we learning? The learning rate is a number between 0 and 1, which can be thought of as much quickly as how quickly the agent of the previous Q value in Q table for the given state actions of the new Q value. So we will calculate the new Q value according to this equation from the formula of calculating the new Q value state of action pair of SA at all this time. So again, we are coming to this Bellman equation with this illustration. This is the old value of Q state and actions, and here is the learning value. And this equation will be clear with this example of lizard again. Just to make it easier, let's assume we have this lizard here. The lizard wants to go to explore and to estimate which value to be done. So let's assume that we are moving this lizard to the right from this box to this here. So we know here is -1, right? Because it is empty. So let's have this discount rate 0.99, and the learning value is 0.7, just assumption to start with that. So just to set these values in these equations, we will get this equation, which is here, because this is the original equation, and here we put these values in this equation. We have it here, but what is the value from this term here, which is the optimal Q state and actions value? Because it is starting from 0, there is no, here the lizard is here, so the state is 0 and the action is 0, so there is no optimal, there is no best, there is no maximum best values previously, because it's starting from 0, so it is 0. But the next state will be generated, it is starting to select. So from this state we'll get -0.7, and here it is this, when the lizard here, it is getting the best new value from state and action is 0.7, -0.7. all right, so now it goes back, or it goes further and compare it with this new Q star SA value, and we'll keep updating this table and fulfilling the previous shown table over here, which is here. This table will be fulfilled until the end. It will see which are the best selective movements to be done and the shortest actions to be selected, so that we get the best result. So far, this is the explanations about the Q-learning, and we will implement this Q-learning with the deep learning. Until now, we are just talking about Q neural network, or RL, with Q-learning. To implement that with RL, we need to add this block, which is deep neural network, to make it easier to instead of having state and actions and then select the path and fulfilling these tables. No, we will just get the state, and then we'll get the estimation of state and actions with the help of deep learning, which is the same equation you see here with the same estimation, but it is with the instead of just having this kind of large tabling, deep learning will provide shortest way to get them together with the matrix equations. And here is a basic illustrations of that, because it sends, it generates these kind of actions and states to provide a better result, and cumulatively with the backpropagation algorithm that will be generated, there will be the agent will understand what are the best actions and what are the best states to be taken for the agent to achieve the best results.